In this lecture, we'll talk about the flyback converter, which is another very popular form of transformer isolated converter. The flyback converter is a transformer isolated version of the buck-boost converter. Now, it turns out that in the buck-boost converter, it is actually easy to add a transformer. Here's a diagram of the buck-boost, and we have a point in the middle of the buck-boost converter where there is already an inductor. And you could simply place a transformer at this point, and the volt-seconds will balance because they already balance on the inductor. And in fact, what we do in the flyback is we turn the inductor into a transformer. It's actually, we often call it a flyback transformer, and it functions in fact more like a two-winding inductor. So here is a way to think about it. Suppose we're in the lab winding an inductor with, say, some length of wire that we wind some number of turns on a magnetic core to make an inductor. And suppose instead of just winding one wire, we wound two. So perhaps it's like we needed a fatter wire or thicker wire to have lower resistance, and we decided to just take two wires and put them together as if they were one and wind them together. Same number of turns. Okay, so I could draw that this way, as is shown in this lower diagram, and it actually looks like a one-to-one transformer. The inductor, though, what we were calling the inductor in our original buck-boost converter, we might call now as the magnetizing inductance of this transformer. So it's like we have an inductor, and then we have a two-winding ideal transformer. Now, so far we really haven't changed anything. It looks more complicated, but it's really just functioning as an inductor with the inductor current splitting in some way between the two windings. What we can do, though, in this case now, is to now break this connection. This changes how the current flows through the two windings, although it doesn't change the sum of the current. So if we have current in this winding, call it I1, and a current in this winding, we call I2, the sum of those currents adds up to the original I of the buck-boost converter. But the difference is that now we have I1 flowing when Q1 is on, and I2 flows when D1 is on. So I is distributing between the two windings in a different way. Now, the way we normally draw the flyback converter is the bottom diagram, and it's nearly the same as the one above it. To get a positive output voltage, what I've done is reverse the polarity, or reverse the dots of the winding. Recall that the buck-boost converter inverts the polarity. If we want our flyback converter to make a positive voltage, then we must reverse the dots, and we reverse the diode direction also, so we get a positive output. And then the other thing we can do, if we like, is now apply a turns ratio. And the turns ratio will let us scale the voltage up and down. And this is the conventional flyback converter. There's one other small change. The order of Q1 and the primary winding are reversed here. We usually do that to put the source of the transistor at ground and make it easy to drive with just a regular ground reference driver. So the flyback converter is a buck-boost converter in which we realize the inductor using two windings that effectively give us isolation and a turns ratio. The flyback transformer then, which is this two-winding magnetic device, can be modeled in the same way as a usual transformer, with an ideal transformer and a magnetizing inductance put in parallel. But now we're using the magnetizing inductance as the actual physical inductor in our converter, and this inductor is designed to store energy. Not only that, but the winding currents look very different than the way they look in an ideal transformer. We never actually have current flowing in both windings. There's either current flowing in the primary when the MOSFET is on, or in the secondary when the diode is on, but we don't have the case that the secondary current equals the turns ratio times the primary current. So the magnetizing inductance is very significant, its current is large, and as a result, we don't see what we would normally expect in an ideal transformer. Far from it. We won't talk about magnetics design in this Coursera course, but I will say that the design of the flyback transformer is very different from the design of a more ideal transformer, such as the one that is in the forward converter. We put an air gap in this transformer that lets our inductance store substantial energy, and its behavior, as I mentioned, is different. Okay, having said that, we can still model our converter in the usual way. We replace the transformer with our transformer model having a magnetizing inductance. We then solve the converter, applying volt-second balance to the magnetizing inductance, charge balance to the capacitor, and so on, and we can get the equations of the converter. So here's what happens during subinterval 1. In subinterval 1, the MOSFET is on, the diode is off, as is usual in the buck-boost converter. And with the MOSFET turned on, then we have the magnetizing inductance connected to VG. And so we will have what VL is equal to VG. We have current flowing around this path. The capacitor current is simply minus the load current, or minus V over R. And the input current IG is equal to the magnetizing current I. We'll assume we're in continuous conduction mode here and apply the small ripple approximation to V and I and get these equations for the first interval. For the second interval, the MOSFET is off and the diode is on. We now get this circuit with the diode connecting the transformer secondary to the output. With the MOSFET on, the magnetizing current cannot flow through VG anymore. In fact, the magnetizing current or the inductor current will flow out the secondary. In our transformer equivalent circuit model, the way this works is that the inductor current or magnetizing current continues to flow, and it flows around this way, around this path. So it will flow through the ideal transformer and come out the dot on the primary side. So on the secondary side, we have current going into the dot equal to this primary current, or I, divided by the turns ratio N. So now the capacitor current for this interval is that secondary current I over N minus the load current V over R, and we get this equation. The voltage on the magnetizing inductance VL is in fact the reflected secondary voltage. With the diode on, we have voltage V applied across the secondary, and that voltage is negative at the dot of the secondary. So it will be negative at the dot on the primary, and the primary winding voltage will be V divided by the turns ratio N. So the inductor voltage is minus V over N for the first interval. With the MOSFET off, IG is equal to 0, and so these are the equations for the second interval. We can again apply the small ripple approximation to replace V and I with their DC components, capital V and capital I. So then here are those waveforms. Here's our VL waveform, our IC waveform, and our IG waveform. So now we can apply volt-second balance to VL. So the average VL is D times this voltage plus D prime times that voltage, as is shown here. Volt-second balance says that that must be 0. We can solve this then for the output voltage. So what do we get? V would be VG times D over D prime times the turns ratio N. Okay, so the output voltage is the input voltage times this buck-boost conversion ratio D over D prime, and then also times the turns ratio N. We can apply charge balance to the capacitor. So the average capacitor current will be D times the value during the first interval plus D prime times this second interval value, which gives us this equation. We can solve that for the inductor current I, or magnetizing current, and what we find in that case is that the magnetizing current, referred to the primary side, is V over D prime R, and then times the turns ratio N. Finally, we can write the equation of IG. The average IG is D times the value during the first interval, I, plus D prime times 0. So we get the average IG is D times I. So those are the equations of our DC model of the flyback. As we've done in previous chapters, we can construct equivalent circuit models to go with them. This first one from the inductor gives us this center loop equation. The second one from capacitor charge balance gives us the output side. And the third equation for the average IG gives us the input port model. So we get this circuit, and finally we can replace the ideal sources with transformers and get an equivalent circuit for the flyback. The ideal flyback has a buck type transformer, and then it's followed by a boost type transformer, and the boost transformer additionally has a turns ratio. So in the end, this is a buck boost converter with an added turns ratio, and the flyback then has its origins, as you would expect, in the buck boost. So the flyback is a widely used and popular converter because it has a very low parts count. It's actually known to be a cheap and inexpensive way with a very small number of parts to build a converter. You can get multiple outputs for very low cost as well. All we have to do is build another output. So we could, for example, have our flyback converter with a transistor, a single magnetic device, flyback transformer, and then one diode and one capacitor for each output, and get multiple output voltages with different turns ratios, and with very low parts count, small converter, get a lot of different voltages. One problem that is known with the flyback converter is a problem called cross-regulation. If we have, say, in 2 turns on this output and in 3 turns on this output, with their respective voltages V2 and V3, we would hope that V3 would be the turns ratio in 3 over in 2 times V2. That's what we would hope, and if we have good cross-regulation, then that's what happens. It turns out with a flyback converter, second-order effects related to the leakage inductances, these small inductances of these transformers, cause the output voltages to differ substantially, and it can make the output voltages highly dependent on load current. So the cross-regulation between the two outputs is not very good, and we usually have to do some more work and more engineering to get a good design. So it's inexpensive, but the performance in that sense is not as good. The flyback is often operated in discontinuous conduction mode. That makes the magnetizing inductance very small, and this transformer then can be very small. And so we not only have small parts count, but we have small magnetics also. You can do an analysis of this converter in discontinuous mode, and it turns out to be to give the discontinuous mode buck boost equations with an added turns ratio.